Okay, I'm going to start by sharing my screen here. So this is the formula sheet that you would find on your TQ. And we're going to talk about all of these things on here today, if we can get there. So first off, anytime we do any calculations with any kind of water or any kind of substance, I do want to start off by saying that we actually do it in STP. Does anybody know what STP stands for? Just shout it out if you know the answer.
Standard temperature pressure.
Standard, that is right. Standard temperature
Pressure.
and pressure. That's right. Standard temperature and pressure. We do all of our calculations based upon this unless otherwise we are told. So let's start with standard temperature. Does anybody know what standard temperature is?
Hey, Doug, real quick.
Yes.
Is there an ILM that relates to what we're doing here? Or is this just review?
This is just review from first year.
Okay.
Right now, so no, we don't have any of that. Does anybody know? So standard temperature is actually 60 degrees Fahrenheit. And there's a metric equivalent to that. And the metric equivalent is usually posted right on the gas pump when you pump your fuel. And it says 15 degrees Celsius, but it's actually more accurately 15.5 degrees Celsius is standard temperature. Now they want you to have that commodity, that petrol, at a standard temperature, because you know that temperature and pressure affect all matter in which it exists. So if we have very high fluctuations in temperature, that fuel will expand and contract accordingly. Yes? Okay. So there is another thing about temperature that you will or should, excuse me, know. So if you want to go from Celsius to Fahrenheit, you're going to have to know how to do this. So what you do is you take your Celsius degrees and you go 1.8 times your degrees Celsius. I'll put a bracket there because we have to do this, and we add 32 to it. And that would come out to our degree Fahrenheit. So let's do that quickly. We will take the 15.5 degrees C and we're going to multiply it by 1.8. And that's going to come out to 27.9. And then we're going to add 32 to that. And that comes out to 59.9 degrees Fahrenheit. So it actually works. And then to go the other way from Fahrenheit to Celsius, the formula for that is you take your Fahrenheit and you minus 32 degrees off it, and then you divide it by 1.8, and that would give you your degree Celsius. So that's standard temperature. The next thing that we need to discuss is standard pressure. Does anybody know what standard pressure is?
Atmosphere?
It is atmospheric pressure, yes. So this is taken at sea level, is standard pressure. And what is that again? Anybody remember?
Atmosphere. So it's
15.7.
Sorry.
It's 14.7 psi. A is the weight of the atmosphere at sea level. So that is the weight of the air that we have on us at sea level. And there is a metric equivalent to that. So that is 101 kPa is the metric equivalent to standard pressure at sea level. Now, there's also another couple of different pressures. Just try to mute yourself there unless you want to talk or cough. That's okay.
Yeah, sorry.
So we also have 29.92 inches of mercury is considered to be standard pressure, or 760 millimeters of mercury. Now, Hg is the chemical symbol for mercury. Now, do we know how these numbers came into effect? Well, let me just explain a little bit. So there was this guy that used a bowl of mercury, and what he did is he took a tube filled with mercury with a closed end, and he put it in the bowl. And he filled the bowl full of mercury with mercury in the tube. And what he figured out is that the mercury at sea level had a measurement of 29.92 inches of mercury going up in the tube all the way to the top. Okay, so it was filled with mercury all the way to the top. So he took this device and he actually went and climbed a mountain. And as he went up the mountain, this actually dropped. So he determined that the higher the elevation, there was less pressure, less atmospheric pressure exerted downwards on this. So this is how we got this 29.92 inches of mercury. And the guy who did this was Torricelli, is the guy that came up with this. So he's the guy that figured out air pressures. Now, it's not super important right now, but I want to tell you that sea level pressures are considered to be from 0 to 2,000 feet in elevation. And high altitude is considered from 2,000 to 4,500 feet above sea level. And anything over 4,500 feet is considered to be extra high altitude. Now, this becomes important to us as gas fitters, because at higher elevations, things burn differently. When there is less pressure, actually flames burn hotter. It is said that you could boil water at the base camp of Everest at 70 degrees Celsius because there's less pressure on us, right? My golf ball flies farther at high altitudes than it does at low altitudes because there's less air pressure or less friction, if you will. So that's just an aside note on there that you would need to know. So while we're talking about pressure, this formula triangle right here, this one right here, we're going to talk about in a second. Okay, so let's talk about pressure first off. I'm going to give you the definition of pressure. The definition of pressure is force per unit of area. Now, the area that we are typically talking about when we talk about pressure is in square inches. For example, we usually express our pressure in pounds per inch squared. Yes, pounds per square inch, or sometimes called PSI. That is typically how we describe pressure. Now, so we need to know what force is then. So the definition of force is actually a push or a pull, or sometimes it's called work. And we express force in pounds or metrically newtons. That's how we typically express force. So it says in the pressure, it says force per unit of area. So this is where we get pounds per square inch. And so that to me makes sense. So when we do this stuff, we use that formula triangle, right? Where we have the pressure up on the top, and pressure is all about height. So that's what the H is equal to height. Pressure is all about the height of the fluid, and then we multiply it by a density. And we'll talk about densities of water in a minute, but let's get into this. When we have height of fluid, if I'm talking about inches, and when I'm talking about this right now, I'm going to talk about water, because this is for hydrostatic pressures, this formula. And hydrostatic means water, and static means standing still. It's not flowing. There is no water flowing when we take these pressures. So if I'm talking about inches of water, that's my height here, I'm going to multiply it by 0.0361 PSI per inch. So that is the number that we will use when we describe inches of water. For example, what is 28 inches of water in PSI? So here's an example. So if I had 28 inches, I will take 28 inches, multiply it by 0.0361 PSI per inch, and the inches get canceled out on that side, and that's going to come out to 1 PSI.
So the 0.0361 is your density.
It is the density of water for 1 inch in height. That is correct.
And so we use that because we're working with water.
That is correct. I will talk about relative densities and that sort of thing in a bit. So we actually don't use a lot of inches of water column. We will if we're measuring very small pressures like gas pressures. And you will learn a lot more about that gas pressures next year, in third year when you do gas theory. We usually talk about head pressure. And head pressure is all about feet. So if I'm talking about feet of water, I will use a density of 0.433 PSI per foot. And this is how we calculate head pressure. For example, if I had a building that was 30 feet tall and I had water exerted, so let me just draw, oh, that's a bad drawing. Let me just draw this building, see if I can here. So if I had a building that was 30 feet tall and I had a gauge on the bottom and this was full of water up to here, I had a gauge on the bottom. I want to know what pressure is on my gauge. I will simply take that 30 feet and multiply it by 0.433 PSI per foot to get me a pressure of 12.99. So almost 13 PSI would be on my gauge here. So I could actually say 13 PSI G. When I say G, it means it's gauge pressure. The atmosphere is not acting on that gauge because it's an enclosed system. Another pressure measurement that you need to know is meters of water. Meters of water, we use it a lot in plumbing theory. The plumbing code book is in metric, as the gas code book is typically in imperial measurement. I know that's kind of awkward, but it is the way it is. So we need to know the pressure of 1 meter of water, which is 9.81 kPa per meter, is the next one that you would need to know. And let's do an example of that. So if I had a pipe that was filled with water and that pipe was 50 meters tall, what is the gauge reading at the bottom? We simply take that, times it by 9.81 kPa per meter. And that would give me a pressure of 490.5 kPa if I had 50 meters of water in a pipe. Now, there is a couple of, there is another one in here, and it is for inches of mercury. So if I had inches of mercury, I would multiply by 0.491 PSI per inch Hg. And that is how much pressure 29 inches will exert. Now, I want to talk about density. So first off, we need to have a definition of what density is. And the definition of density is a mass per unit of volume. And as you know, water has a given densities that we need to know. As plumbers and gas fitters, it's important that we need to know the densities of water. So first off, we're going to do the one we already know, 0.0361, and I'm going to say pounds per cubic inch is a density of water. Now, it says mass per unit of volume. Mass is either in pounds or kilograms, and unit of volume, it has to be in cubed to be a volume. Water also has a density of 62.4 pounds per cubic foot of water. Water also has a density of 1,000 kilograms per cubic meter of water. And these numbers shouldn't be new to you. You should know these numbers already. There is another couple of densities that I want you to know, and that is there is 10 pounds in 1 gallon, and that is imperial. So this is a mass, and a gallon is a volume, so that is still a density. And the next one we need to know is 8.33 pounds in a gallon, and that is for US purposes, and that's for United States. You may hear me refer to the US as excited states because they're always excited about themselves. And why do we need to know this number right here? Does anybody know why?
To calculate with our triangle.
Well, 8.33 pounds per gallon US. We need to know this
Missing link.
number because the US has more guns than us. No, that's not true. Well, it is true, but they're our biggest trading partner, and we buy a lot of our materials and a lot of our stuff from the US, and they use their US measurement for gallon, and that's why we need to know it. It's our biggest trading partner, quite frankly. So that's why we need to know it. And most all of our pumps and circulators are done in US gallons. So that's why we need to know that number. So that's the densities of water that you need to be concerned about. We also have some densities of air that we need to be concerned about a little bit too. And the densities of air are 0.076 pounds per cubic foot. So that's the mass of what air is. And there is a metric equivalent to that, which is 1.29 kilograms per cubic meter is what air weighs. Now, to do any density calculation, we use the formula triangle where we say the mass divided by the volume is equal to the density. So M is equal to mass, and the mass is always in pounds or kilograms. The volume is either in inches cubed, cubic feet, or meters cubed. And then the density is always a mass per unit of volume. For example, I could find out Doug's density. We could figure out how dense I am. Well, wait a second. That didn't sound correct. But anyways, let's find out how dense Doug is. My mass is actually 170 pounds. COVID hasn't been great to me. I'm gaining a little weight around right around the middle tire, so to speak. But my volume for me is about 2 cubic feet. I don't have a huge volume. So what is Doug's density? Well, let's take the mass divided by the volume. So that comes out to 85 pounds per cubic foot. So that's the density, that's Doug's density, that's my density. Now, let me just ask you this. Am I heavier than water? Am I heavier than water? Just shout it out.
Yes.
Yeah.
Yes, look at how heavy water is over here. I'm going to just kind of circle this. Look how heavy water is over here. You see that? 62.4 pounds. I am actually heavier than water. And I could figure out by how much heavier than water I am by simply taking my density and dividing it by the density of water. I could find my relative density. So we'll take 85 and divide it by 62.4. Doug's relative density is 1.36. And this means I am 1.36 times heavier than water. So what also that means is that when I get into a swimming pool, so if I had a swimming pool and it's full of water and I jump into the pool, guess what happens to Doug when I get into the pool? I sink because I'm heavier than water. I sink when I get into the pool. I don't float like some people. I know people that are way heavier than me, but they have a bigger volume than me. And if their relative density is less than 1, they will float. It's kind of a buoyancy kind of rule. And we're going to cover buoyancy in the near future. So I'm just going to pause here for a second. Okay, where we left off is we were talking about densities and relative densities. So as you can see, we figured out Doug's relative density here. So we should actually figure out what relative density is. So the definition of relative density, and sometimes this is called, you may see this language, specific gravity. So all or most substances are giving a relative density or specific gravity. And what this is, it's how many times heavier it's how many more times heavier a substance is compared to a standard. And the standards in which we talk about are actually right here. It's air and water. A little bit farther over here. Air and water are the standards in which we compare solids, liquids, and gases to. So solids and liquids will always be compared to water. And gases are compared to air. So all gases are compared to air. For example, if I had a solid that was 3,500 kilograms per cubic meter, and I wanted to know the relative density or specific gravity of that substance, what we do when we want to find a relative density, we will divide by the standard. And the standard, when we're talking about metric, is 1,000 kilograms per cubic meter. So this object has a relative density of 3.5. Now, there is some relative densities that you should know. For example, CH4. Well, first, water has a relative density of 1. Air has a relative density of 1. CH4, which is natural gas, has a relative density of 0.6. C3H8 as a gas is propane, has a relative density of 1.5. So is propane gas heavier than air? Yes, it is. So propane gas, because it's heavier than air, you cannot have a propane vehicle in an underground parkade. So this is one of the reasons why you can't have that. So propane, as you know, comes in a liquid form. And propane as a liquid has a relative density of 0.51. So here is a question example for you. If you had 10 gallons imperial of propane liquid, I want to know how much does it weigh? Well, first off, we compare everything to water or air. So I have to know how much 10 gallons imperial that water weighs. I know that there is 10 pounds in a gallon for water, and I have 10 gallons of that. So that's going to equal 100 pounds is what water is. Now, propane liquid over here has a relative density of 0.51. So that tells me it's 0.51 times heavier than water. So 10 gallons of propane liquid is going to weigh 51 pounds. So that's how we do that. And that is how relative density works. It is first find the mass of the standard, then multiply it by the density. I will do another example here. First, I'm going to say I have a pipe filled with liquid. There's my pipe. It's pretty shaky. And I have a pressure gauge at the bottom. Now, this pipe is 75 feet tall, and it's filled with glycol. And this glycol has a relative density of 1.66. It has an RD of 1.66, this glycol. I want to know what my gauge pressure is on that gauge. I'm going to give you a minute to calculate that. If you have an answer, just put it in the chat. Just put that in the chat there. That's, oh, I gotta open the chat so I can see it. And I still can't see it. No, Brett, no. No, that's not right. Anybody else yet? Put it in the chat. That's right. That's right. Justin Ale. I don't know who Ale is. A-L-E? Changed your name to something. Justin, that's correct. Okay, so how we do that is first we have to get the pressure for water. So what we do is 75 feet multiplied by 0.433 PSI per foot. And that is going to come out 70 times 0.433. That's going to come out to 32.475 PSI. And now I simply multiply that by the relative density. It's 1.66 times heavier than water. And that comes out to 53.9 PSI. G is going to be on that gauge. And that's how we figure that out. Okay, we're going to get back. I'm just going to pull this down a little bit so I have a clean area. So there is 12 inches in 1 foot. Is that correct? You should know that. It's pretty easily to know. There is also 1,000 millimeters in 1 meter. There is also 100 centimeters in a meter. There is 10 decimeters in a meter. In 1 square foot, so if I had a square and it was 12 inches by 12 inches, that would be 144 inches squared. Or if this is 1 foot by 1 foot, this would be 1 square foot. So I could say there is 144 inches squared in a square foot. Now, if I had this in a cube, and that was 12 by 12 inches by 12 inches, that would be 1,728 cubic inches. And that's 1 foot by 1 foot by 1 foot. That's 1 cubic foot. So I could say there's 1,728 cubic inches in a cubic foot. That's another number you need to know. I know this is review, but that's the way it goes. And I'm going to break down inches. In 1 inch, we would have 8/8. So in our plumbing trade, in our plumbing gas fitting trade, if we're using imperial measure, we use stuff like halves, quarters, eighths, sixteenths. And listen, if we go any farther than sixteenths, I usually throw my tape measure at somebody, because really, if you're using your tape measure and you start to go 30/2 of an inch or 60/4, yeah, that tape measure is going to come screaming at your head, because there's no way I'm cutting anything that's close, right? So, but we need to calculate some of these things. For example, 1/8, if I'm talking about inches, as a decimal point, we take 1 and divide it by 8, because this is the numerator and this is the denominator. Remember all that stuff? So 1/8 is is equal to 0.125 inches. Yes, we know how to do that. Okay, excellent. Now, just to bring you back into doing fractions quickly, I want to know what 137.5 inches. I want you to express that in feet, inches, and to the nearest half inch. So way to do that is to take this, if I got to convert this into feet, I will divide this by 12 inches per foot to convert it to feet. That's going to come out to 11.458 feet. So that's 11 feet. And now I have my 0.458 feet times that by 12 inches per foot. And that's going to be 5 inches because this comes out to 5.5 inches. And I know that is a half. So 137.5 comes out to 11 feet, 5.5 inches. So I'm going to expect that you guys can convert inches into decimals and decimals into fractions, etc. Does anybody need more help or more examples on that? Just shout out yes or no. Okay.
Maybe there's one more. I got a little lost there.
Okay, so let's do something like this here. I'm gonna just zoom in here. If I had 0.79 inches, less than 1 inch, and I wanted this to the nearest 16th. So this is my denominator, and I want to know the numerator. So if I had a decimal of an inch or less than 1, I simply take that, multiply it by the denominator, and the answer is my numerator. So that comes out to 12.64. This rounds up to 13. So 0.79 inches is equal to 13/16. So I simply take my decimal of an inch, multiply it by the denominator, and the answer is the numerator. Let's do another example. 0.125 inches, and I want it to the nearest eighth of an inch. I simply take that decimal of an inch, multiply by the denominator. The answer is my numerator. So 0.125 inches is equal to 1/8 of an inch. So that is a quick way of taking decimal of an inches and putting it into a fraction form. Cool? Good? Yeah? All right, all right. Now, what I want to do is I'm going to put a couple of questions up here. Actually, what I should do is I'm going to import something here. So this formula triangle book that is in D2L gives you these formulas that you can use. So perimeters right now, perimeters is really the outside of this, and that's what perimeter means. Area is length times width, And this is divide. As you can see there, perimeter is adding all the outsides to it. I don't think I need to discuss that too much more. Circles. Circles, it's important that we know what pi is, and pi comes out to 3.1415926. Hang on a second, this is out of control. So when we use pi, either we use it on our calculator button or we will use 3.1416. Anytime we start to use these decimals, for math purposes only, I want you to go 4 decimals. Okay, 4 decimal places when we do our math. Listen, our numbers may vary slightly because if you use pi on your calculator, it's actually 3.1415926. I don't know, 54. See, there's slight differences in here compared. So we need to know that if our answers are close, we're going to call it good. All right. Does that make sense? If we're close, we're going to be okay. So anytime we use pi, we're going to use the 3.1416, or else you use the pi button on your calculator. Diameter is the entire length of this, and the radius is half of the diameter. So I'm going to ask you a question here. I have an outside diameter of a pipe that is, let's say, 10.85 inches. I have a wall thickness of, let's go 3/16 of an inch. I want to know the inside diameter of my pipe. So if you know anything about pipe, which you should, I said the OD was 10.85 inches, and I want to know the inside diameter here. But I said that their wall thickness is 3/16 and 3/16. There is 2 wall thicknesses on a pipe. So I'll take 3 and divide it by 16 just to get this fraction into a decimal. And that will equal 0.1875. And I have 2 of them. So I will times that by 2. And that equals 0.375 inches is my wall thickness. So now I'll take my outside diameter minus my wall thickness. And that would give me my inside diameter of 10.475 inches. Okay, don't forget that there's always 1, 2 walls to a pipe. Okay, if you're doing inside and outside diameter. Good. All right. Now, these formula triangles are pretty good. I like them because of the fact that they have on here points to remember. Okay, we already know there's 1,000 liters per cubic meter. There's 7 point, well, do we know that's 7.5 US gallons per cubic foot? I never talked about that. And then 6.24 gallons per cubic foot. So to get these numbers, I know that there's 62.4 pounds of water in 1 cubic foot, yes? And if I wanted to know the US gallons, we will simply divide by 8.33 pounds per gallon. And then that comes out, as you know, we remove those. That's going to be 7.5 gallons per cubic foot US. So in 1 cubic foot, we can get 7.5 gallons. So that's where that number comes from. And for the imperial measurement, it's 62.4 pounds per cubic foot of water. And I know that there's 10 pounds in 1 imperial gallon. So that comes out to 6.24 gallons per cubic foot imperial. And what we are talking about right here is now capacity. Capacity is really defined as how much does the object hold. And this capacity can be in gallons, it could be in pounds, it could be in kilograms, it could be in liters. So the capacity is a volume of liquid or air or something that this vessel holds. And the vessel will be in a volume form, and typically cubic feet or cubic meters. And as you can see, in a cube right here, this is a cube. This is our formula for a cube for a volume. Its length times width times height is the volume. So let me ask you a question as an example. If I had a container that holds 1,800 liters, and I needed to build a space to hold that container. So I'm going to draw a container here if I can. There we go. It's not very good. And I will do. So this container has to hold 1,800 liters. But here's the issue. The bottom is only going to be 0.25 meters by 0.25 meters. I want to know the height of my container. So I was given first off a capacity up here of 1,800 liters. Can I get a volume from that capacity? Yes, I can. So I take my 1,800 liters, and if I divide it by, if I know that there is 1,000 liters in a cubic meter, I can get a volume of 1.8 cubic meters. So that's the volume that that container has to be. I know to get volume, its length times width times height is equal to my volume. So I will just put these numbers into my equation. So when you guys are doing this, I would particularly like to see that you write the formula down and then you put your numbers in. So there's my length, there's my width, times my height, which I don't know what it is equal to 1.8 cubic meters. So there's my formula. Now I want to get my height by itself. So what I'll do is I'll multiply these two things together and I'll rewrite this. So 0.25 times 0.25. And that is going to equal 0.0625 meters squared times my height is equal to 1.8 cubic meters. So I want the height all by itself. And what I do is I simply have to take the 0.0625 meters squared. If I divide it by that, that is going to equal my H. But if I do it to one side of the equation, I must then divide it by the other side. So my height equals now 28.8 meters. So that's the height of that container. So volume of a cylinder is also very important to us. Cylinders also mirror what pipe is, right? Pipe is really just a cylinder. And the volume of a cylinder, the formula for the volume of a cylinder is pi r squared times height is equal to the volume of a cylinder. So I have a cylinder here, and I'm going to tell you that this cylinder is 20 feet in height. So the height is 20 feet, and it has a diameter. I'm going to say 6'3" is the diameter. And I'm going to say this is filled with water. I want to know how many imperial gallons does this hold? So I'm going to give you a few minutes. Okay, so here's my formula. I've wrote it down. I'm going to write my parameters in, and I would suggest that you do the same. So my diameter, if I took 3 divided by 12, that's going to be 0.25 feet. So 3 inches by 12 inches per foot. So my diameter ends up being 6.25 feet. The radius is half of my diameter. So my radius is equal to 3.125 feet. My height is 20 feet. So now I can put my numbers in my formula to find my volume. So that is going to be 3.1416, that's pi, times 3.125 squared times my height, which is 20 feet. So if I multiply this out in my calculator, I'm going to come up with 613.5923 cubic feet. And now I know that there is 6.24 gallons in 1 cubic foot. So I multiply by 6.24 gallons per cubic foot, and that's imperial. And that gives me 3,828.8, I don't know, 2 gallons.
Doug, can I ask just one quick question?
Sure thing.
Just back, do we need to memorize the actual like volume units, like the 6.24 gallons per?
Yeah, you do need to know the densities of water and air and pressures. Yes, you need to know all those, Connor. Yeah.
Like it will be required for us to memorize them on tests. Like there won't be an actual like formula sheet for that part.
You'll have the formula sheet, but the formula sheet you get would be this formula sheet that we started with. Where is it? Over here. This is your formula sheet that you get.
Okay.
And that's it. You need
Okay,
to know
yep.
all your other numbers.
Okay.
Okay, excellent. Okay, so we're going to continue on. And where we're going to go is hemispherically ended tanks is the next thing I want to talk about. Now, here's the thing. We have to do two separate things in here. First, I'm going to give you the formula of a sphere. So if we had a circle or a sphere, so if this was like a sphere, so this is a volume, like a big ball kind of thing. The formula for the volume of a sphere is labeled as 4/3 pi r cubed. That's the formula for a sphere. So that's a sphere. And then we have the formula for a cylinder. And we know that to be pi r squared times height is the volume of a cylinder. So now the formula for the volume of a hemispherically ended tank is adding these two together. And then you're going to ask me, maybe not, but why do we need to know hemispherically ended tanks? Well, hemispherically ended tanks come in propane tanks, just like this. And we need to know the volume of some of these things. So I'm going to break this down. I'm going to do a couple of questions according to volumes of these tanks. First off, I'm going to give you some parameters. So I'm going to tell you that the overall length, and that's this number right here, this number is the overall length of the tank. And I'm going to give you that overall length of the tank. I'm going to call it, let me get back to there, 15 feet. And then I'm going to give you the diameter, and I'm going to say the diameter is 5 feet. So at this point, I would write that in. So my overall length is 15 feet. My diameter is 5 feet. What would that make my radius?
2.5.
2.5 feet is my radius. So I'll write that down here. Radius is 2.5 feet. It's half of the diameter. So having a look at that, you see this next measurement here, this length or height. What is this measurement in here? This length or height. Do you see that?
10.
That's going to be 10 feet. That is correct. Thank you. Because we are not counting the ends or the hemisphere on here, or the sphere, if you will. So this height and this length goes right here. So these match. Let me just outline that just quickly. This height for the cylinder is this height here. Okay, because once we remove the sphere off of that hemispherically ended tank, we only have a cylinder left. And that's where the cylinder volume comes in. So we're going to take the volume of the sphere and add it to the volume of the cylinder. So let's do some of this math. So if you do 4/3 in your calculator, it comes out to 1.333. Repeating, we'll go 4 decimal places. So right now we're getting the volume of the sphere. So that is times pi. And we're going to multiply that by my radius cubed. Okay. I shouldn't put cubic feet there, but that's okay. It's going to be radius cubed. So if I get my volume on my sphere, that is going to equal, let me just do that quickly, 2.5 cubed times pi times 1.3333. We're going to be really close together, or close enough to call that 65.45 cubic feet is the volume of the sphere. Now I'm going to get the volume of the cylinder. There is the volume formula. It is 3.1416 multiplied by 2.5 squared times my height. My height here is actually equal to 10 feet. Remember this height up to here. Times that by 10. So the volume of my cylinder only is 196.35 cubic feet. And now I'm going to take my volume of my sphere and add it to the volume of the cylinder to get the total volume of 261.78 cubic, or 8, I should say 8 cubic feet. So clear? Not too bad, huh? Let's do another example of this with different numbers. And I want to get rid of that. Oh, there we go. There we go. Okay, so my new parameters here, I'm going to give you some measurements, and I want you to do this on your own for the minute here. And I'll put in the numbers. So I have an overall, oops, I need a pen. Overall length of 24 feet. I'm going to give you a diameter of 6 feet. I want to know how many US gallons of water that this tank will hold. How many US gallons of water will this tank hold? I'm going to give you a few minutes to do this math. Okay, I left you off with asking you how many US gallons would this hold with these parameters. So my overall length is 24 feet. My diameter is 6 feet, which makes my radius 3 feet, and which makes my height 18 feet. So the radius is 3, and my height here is 18. So the formula is 4/3 pi r cubed plus pi r squared times height is equal to the volume of this hemispherically ended tank. So I'm just going to write these out. So 1.3333 times 3.1416 multiplied by 3 cubed plus 3.1416 multiplied by 3 squared times 18. If I do this on my calculator, it's going to come up to 113.09 cubic feet. And this one for the cylinder comes out to 508.93 cubic feet to give me a total volume of 622.028 cubic feet. And now I simply multiply that by 7.5 US gallons per cubic foot to get me a total gallon of 4,665.2 US gallons.